Hello, this is Mariam Qasim, and this is my fourth lab for Physics 2211, Oscillations. Here is our index. We'll have an introduction, then explanation for the physics principles, the experiment, the code, the comparison between the theoretical and experimental model, and finally a discussion. For our introduction, the purpose of the lab was to track and analyze the motion and position of an oscillating mass. Our aim was to have the experimental model created using tracker as accurate and precise as the theoretical model created using GlowScript. Our main result was that we've produced similar graphs for both the experimental and theoretical models, and we've also found out that the energy principle was obeyed. As for the physics, we have two main principles. First, Newton's second law, more often known as F is equal to ma. Using that, we were able to obtain the velocity update formula and the position update formula. The second principle is the energy principle, which states that energy is neither created or destroyed. We'll also be using the equations for kinetic energy, gravitational potential energy, and elastic potential energy, which respectively are a half mv squared, mg delta h, half ks squared. We'll also be using the time period equation, which relates t to the mass and the spring constant. T is equal to 2 pi square root of m over k. Here is our experiment. We used a spring, a mass, a clamp stand, a meter ruler, and a video camera to record this. Our system is the mass, spring, and earth, and our surrounding is the air. On the bottom right, we have the results. You can already see that we've obtained pretty consistent oscillating graphs for both the x position and the y positions. Moving on, here is our GlowScript code. We first updated our ball's mass to 0.402 kilograms. We also updated the ball's position from tracker, finding the initial x position and the initial v position. We also updated our spring constant by using the time period equation and averaging first by averaging the time periods and then using the equation to obtain the spring constant. We then used the spring constant that we found to find L naught, and then we updated L hat, S, as well as all the energies using the energy equations that were presented in the physics principle videos. We also updated the limit for the while loop by changing the length to 9.5 seconds because that was the length of the video. We also updated our F-grav and F-spring by using their respective equations. And then we found F-net by adding those two forces, and then updated all our values so that we can use them in the next iteration. Here's our GlowScript results. On the left-hand side, we can find the final movement of the ball, and on the right-hand side, we can find the graph for all the energies. We can immediately see that the energy principle was obeyed, as our delta E was consistently 0, which suggests that there were no energy increase in the system or decrease at all. We can also see that our delta U spring and delta U grav are equal and opposite in magnitude. As for the delta K, the magnitude of the change in values is a bit smaller. Here's the comparison between the experimental and theoretical model. For the x position, we can see that there's a slight change, a slight shift in our graphs. But for the y position, even though there is no shift, the amplitude is slightly different. And that could be because of multiple errors that we'll be explaining next. But overall, we were able to obtain similar results. For our discussion, the sources of error could be because we incorrectly identified the center of mass on tracker and then therefore updated the wrong positions. We could have also found incorrect k values because we only averaged out 3 time periods and not more. And since we used that k value to find L naught, our L naught value could also be wrong. So what does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. Well, we already said that the energy principle was satisfied, and that is because the delta E was always 0. No energy has escaped, in quotation marks, or lost, which means that the energy principle was indeed satisfied. Next, using the data you obtained in Tracker, make 2 separate estimates for oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the 2 estimates and discuss. So I used the same method to find the period of oscillation for both the x and the y, and that's by averaging out 3 time periods, and I was able to obtain 1.615 seconds for the x values and 1.52 seconds for the y values. The change, even though it's quite small, it's only 0.1 seconds. That could be because of the errors we mentioned or because of drag. But overall, they were pretty similar, which is what is expected. Thank you.